All right, good afternoon everybody, thanks for coming back. Now the afternoon session is moving from physical layer rather to propagation and coverage issues, so it's my great pleasure to introduce Guillaume, my good friend from old and wild times at France Telecom, where we jointly supervised an untamable PhD student, published a lot of papers together, so we have known each other now for a few years, and Guillaume has a very strong physical layer background, including cognitive issues, so he knows a lot about systems, cross systems as well, including cellular Wi-Fi. He's a professional in propagation, so we're going to hear a few words, a few slides about the propagation issues we face in femtocells, which are quite unique as such. So I'm going to leave the floor to you and to your presentation, Guillaume. Thank you.
Thank you. So first of all, it's supposed to be okay. That's good. Okay, so first of all, I'd like to thank Misha for inviting me to this nice winter school. So I will give a talk on coverage issues for femtocells. So I'm a member of the City Laboratory in INSA Lyon in France, and we are involved in the iPlan project, which is an European project on developing some new tools to help for planning and optimization of femtocells. So I will go fast on first slides because I guess you already have a lot of information about how we want to build femtocells. So I will skip that. I think it's not necessary to see another time all this, but I just want to go to this. What are the key points that we have from the coverage prediction point of view for especially small cells and particularly femtocells? So the problem that we have is to be able to predict correctly not only the coverage of the macrocell plus femtocells, but also the interference between all the users, the femtocells and the macrocells. And we have some problem about how to manage the planning and the optimization, the resource allocation in this kind of networks, how to take into account the ability of controlling the power of emission of different femtocells inside a macrocell, for example, and of course the wide problem of self-organizing networks. So this is a global problem for all layers in the network, but particularly for the physical layer point of view, we need to be able to predict the radio link between not only the base station and the user, but also the base station and interfering users between other users, etc. So we have a lot of different kind of channels that we need to be able to predict correctly, particularly classical outdoor scenarios like we are used to find before in classical cellular systems, but also, of course, indoor scenarios like in wireless LAN systems. But now we have to face a lot of other combined scenarios with how to predict outdoor to indoor propagation from the macrocell inside the house, for example. How also to predict the way that the wave coming from the femtocell inside the building will go through the windows and interfere with the macrocell. And of course, a lot of declination of this kind of problems. And for example, in a residential area, that we will have some links like indoor to outdoor to indoor again, and an interference between two femtocells in two different houses, for example. So here again, I will skip quickly on that because you already know that there's, depending on the kind of standard that we will use for femtocells, UMTS or LTE or LTE-Advanced, we'll have different ways of managing the users and to plan the allocation of resources, of frequencies between the different users or different femtocells. But in any kind of scenario, we will need, if we want to predict correctly what will be the behavior of the network, to know what is the behavior of the radio physical channel. So, of course, when we want to increase the performance of the links, we will need to manage correctly the planning of the different resources between users and between femtocells. So we need to know exactly what is the possible interference between all the systems. So I will start with a simple and global view of physical phenomena which will be involved in the propagation mechanisms. And after, I will detail more on what are the tools that we can use to predict efficiently the radio link. So first, of course, I guess for most of you it's obvious, but I will try to detail a little bit. We have different kind of phenomena that will influence the radio link. So when we use a base station, for example here, emitting radio wave in the environment, we'll have direct connection between the base station and the mobile user. But we can have also some other phenomena like reflections, like transmissions, refractions, diffractions also. So we have different kinds of links, line of sight links, non-line of sight links, with a lot of different behaviors. So mainly we will speak in terms of path loss, shadowing, and fading. So the first and simple way of predicting what will be the received power of a system is to use the simple free space freeze formula, which is well known. It details what will be the received power depending on the wavelength, lambda, the distance, r, and the antenna gains at the emitter and the receiver, and of course the emitted power. This is a very simple view because it supposes globally free space. Just some words about the antenna gain. Of course, lots of work when you consider at the network level what will be the connection between different nodes and different stations. You will consider often that antennas are omnidirectional or isotropic. Of course, when you want to have some more detailed view on the mechanisms, you need to take into account that the antennas are not perfect, have a particular radiation pattern, so you will use a particular gain function depending on what are the different directions which are privileged by the antenna. So globally, the gain function describes what is the spatial filter that you use with the antenna to increase the power in certain directions and decrease it in other directions. Of course, it's also take into account possibly some losses in the system due, for example, of the materials that you use to construct the antenna, but also on problems from the electronic point of view of matching between the antenna and the system. After that, when your antenna is able to emit the radio wave, you will face three kinds of attenuation on your wave. The first one is a simple path loss. So I will detail more further. After that, you will have the problem of shadowing due to obstacles between the emitter and the receiver. So this is quite a slow variation in terms of distance, for example. As you can see here, we will have some slow variation due to the change in the line of sight between the emitter and the receiver. And after that, we'll also face another big problem, which is fading. So fading, now it's a very fast variation on the received power due to the multipath behavior of the link. So when you have a lot of reflection on the different walls of obstacles, you will have a very fast variation of the received power. Of course, all those phenomena are combined, and when you measure, for example, the received power varying the distance between the emitter and the receiver, you will have the combination of a global path loss, but also a slow envelope of shadowing, and around that, a fast variation due to the multipath behavior, so the fading. So we can give a more precise formulation of the Friis formula, adding some terms. So we can have here a long-term attenuation which is relative to the shadowing. We have also a term relative to the fading. I also notice here that I give an R to the power of n. It was square before. I will discuss it after. And also a k constant, which also is relative to particular environmental conditions. So a little bit more in detail. So before detailing the physical phenomena and the description that you can give, just some quick words about the way that engineers, yeah, excuse me.
Those alpha values you just showed, are those random variables or constants?
It's not random, but it can be described in times or in space, depending on what are the parameters of the budget that you want to explain. So of course it varies in space and in time, or also in frequency, all those parameters. But here is just a snapshot, as you have seen here. Okay. For example, it's depending on lambda, so it's for one frequency. And of course, for one distance r. So all the parameters could be could evolve depending on the kind of links that you have. Yeah.
On your previous slide about the antenna gain.
Yeah.
The previous one more back. Yeah, sorry.
This one?
Yeah, this one. Here means the gain is function of directivity, which is p. Yeah. Where directivity of the antenna determines the gain. My question is from the point of view of self-organization or beam forming or energy saving. When you make your antenna more directive, then you have more gain.
Yeah.
Okay.
Of course.
So to have the same EIRP, effective isotropic radiated power, if you make our antenna more directive, are we able to save some power?
Yeah, of course. So it depends on the way that you want to build your system. But globally, of course, even if I go back to this formula, if you change something in the gain of your antennas, as standards give an IRP limit, the limitation will move from the emitted power to the gain. If you increase the gain of your system, you will have to decrease the emitted power.
Yeah, but
so here, yeah, the point is here, even if it's called emitted power, it's the power that you give to the antenna.
Yeah.
So after you have the filter of the antenna. So it's a combination of PE and GE which builds the ARP.
I'm trying to understand, if we have one omnidirectional antenna with say 8 dB gain, okay, to cover a cell radius, okay, instead of that we deploy 3 sectorized antennas, each of them having 18 dB gain. So apparently we have given a 10 dB gain to each antenna, but at the same time we need to transmit on 3 different antennas. So which of these scheme is more energy efficient? Based on means your understanding of antenna, does antenna directivity preserves the energy?
For the same coverage,
Yeah, for same coverage.
You will save power if you have more antennas, because you will increase the gain of each one by using sectorial antenna instead of omnidirectional antennas. So you will save some power.
Same. Yeah. Okay. Okay. Thank you.
So this was just to show that depending on the kind of people you discuss with, they will consider differently the channel. For RF guys working on a system, they just want to take into account that you have a certain level of power at the receiver, and depending on the global performance on the RF front end, you will need to ensure a certain SNR at this level to be able to, after digitizing, retrieve the information to guarantee a certain bit error rates in the system. If you discuss with digital processing guys, for example, they will just consider the whole behavior of the antenna plus the channel as a big filter with different parameters depending on space, time, frequency, eventually polarization also. So everything will be described as process depending on the attenuation, the shadowing, the fading, etc., etc. Here I will just address the problem of how can we model correctly the radio channel. So I will not discuss of the MAC layer, of digital baseband processing, or an RF problems. There was a very good presentation this morning about those problems. I will try to address what is a good way of describing the radio channel, and particularly emphasis on femtocells. So with very simple general models used from decades, we can describe very simply the path loss. So as before in the first formula, we can consider the free space case. Here we'll only have 1/d square attenuation. We can add something more realistic, which is this power n here instead of square. We can describe with this n different kinds of environments. As you can see here, for example, we have a very particular case when you have some waveguide effects, for example, in long corridors or things like this. You can have something lower than 2. But mainly in classical environments, we will have for mainly line of sight case an n between 2 and 4. And for 9 line of sight cases, we'll have an n between 4 and 6. So with this kind of description, we have still a very simple and very fast to compute formula to estimate what is the path loss between an emitter and a receiver. But it's not accurate at all for very dense phenomena and dense environments. It has been applied for wireless LAN plannings, for examples. But already to increase a little bit accuracy of what we describe, particularly for outdoor cellular scenarios, you have some dual slope path loss models. We describe 2 different regions. One first region from the emitter to a certain breakpoint with an n1 exponent here, and a second region with an n2 exponent. I will explain why just after, but you can see that here we have 2 different kinds of path loss depending on the distance from the emitter to the receiver. So mainly, I will explain this problem from the ground effects and the combination of the direct link direct line of sight link between the emitter and the receiver, and just one reflected link bouncing on the ground here. So it's very easy to express. I will not detail the formulas. It's quite simple, but I will not spend too much time on that. But we can easily compute, or no, not compute, calculate by hand. What is the combination of a direct link, so the emitted electrical field in line of sight between the emitter and the receiver, and a second path, which is just this path reflected by the ground. When you express that, you have the combination of those two rays, and you can express very simply the path loss with this kind of formula, where you have a constant plus a term like in free space with a 20 log of the distance over lambda, and a term here depending on this phi here, which is relative to the distance, the delta here, so the difference in height between the emitter and the receiver.
So the reflection coefficient is assumed to be 1?
Yes, there it's a perfect reflection.
Okay, no absorption.
No.
Okay.
So just with this formulation, we show that if you increase the distance while, sorry, I skip back. But here, mainly, the problem is that the combination on the direct line of sight and the reflected ray, you have a difference in terms of phase between the two vectors, which could be a covariant addition or uncovariant. And then, after a certain distance, the difference in phase will produce that instead of having a 20 log of the distance, we have a 40 log of the distance. Perhaps with some illustration it's more easy. So here I give a very simple example of an old GSM system. So with a wavelength of approximately 30 centimeters, with a height of the emitter of 15 meters and the height of the receiver of 1.5 meters. Here, if I give the path loss of free space model, you have the blue line here. So here you have the power, the attenuation, sorry, in dB, and here you have the distance in log. So with the free space model, you have this behavior. With two-ray model, you have this behavior. And when you plot with the assumption of a perfect reflection of the ground, you have this light blue curve. And as you can see, you have globally the behavior of free space till these breakpoints, and after that you follow the two-ray model. And practically, when you consider a real ground, so not a perfect reflector, you see that you follow the same behavior with first a 20 dB decrease of the path loss, and after the 40 dB here. So just to summarize, you have globally 20 dB by decade. That means that each time you multiply by 10 the distance, you lose 20 dB more on your power. And after that breakpoint, you have this curve, so 40 dB by decades. So this is a very simple formulation on the propagation for long-range system. So here is a little table of some values of this path loss exponent that we can find in different kinds of environments. So you can see that you have, depending on the kind of scenarios, urban, dense urban, microcells, etc., you will have very different values of this path loss. So I will detail after what are the more accurate models that you can use with a simple formulation with only path loss. But one point is that with this kind of description, of course, we have a very strong limitation in that we are not able to consider diffractions. So, for example, in that case, if you have the emitter here and the receiver here, of course, with this kind of model, we will consider that there's no transmission at all, because you have something here, which is an obstacle for the line of sight. And we all know that in practice, we have some diffractions here, so we still have some power received here. Of course, not necessarily the same amount of power that in the line of sight, but we can receive the signal. So, of course, diffraction is also an important part of the process of radio wave propagation. Also, we can try to describe the time domain behavior of a link. We have this received power described by path loss, eventually shadowing and fading. But also, if we consider in time domain, when you emit a symbol with your system, what is the way that you receive the signal? As we have multipaths, so reflections, we will receive the same information directly with line of sight, but also reflected by the walls and different obstacles. But all that received information will not appear at the same time exactly. So that's a description of the delay between the first path that we will receive and reflected path that we will receive just after. That's why we differentiate in the description of the channel the delay and the time. All could be described in seconds, but it's not the same scale. The delay is just for the, let's say, the same symbol, what are the different paths, and after the time, what is the behavior of this construction of the links evolves in time. This graph describing, which is called the bellows functions, that shows that we have a dependence on the behavior in time, the behavior in frequency, and that we can describe by transforms between those terms and change the space that we want to analyze the system. So, for example, the impulse response of a channel, which can be described as the sum of different paths that arrives to the receiver, can be expressed very simply like this. Each path represents a particular behavior of the link reflected and arriving at the receiver with a particular amplitude and particular phase. So we can have a transect function expressed in time and delay, but we can also express it in frequency and time, or in frequency and Doppler, or in delay and Doppler. So that is the purpose when you do some channel sounding to characterize a channel. We'll try to have this kind of graphs which represents the behavior of the link. So what we expect from that is not only to have some nice colors on the graphs, it's also to be able to dimension a system. For example, from that we can extract some value of current time, current bandwidth of a system, and being able to describe what is the time where the channel is stable. This is a definition of coherence time. When you want to send a message, send an information, and try to use the description of the channel to equalize at the receiver, you need to dimension the time when you send this information, depending on the way the channel will vary. Same thing for the coherence bandwidth, particularly when you use some OFDM systems like we do in LTE systems. While you will use a wide bandwidth with a lot of subcarriers, if you have a very narrow coherence bandwidth, you will have a completely different behavior on each subcarriers in the systems. So we need some description of this behavior in frequency domain, in time domain, to be able to evaluate what could be the performance of the system in different kind of environments. So here is an example of a tap delay line description of different paths arriving at the same receiver. So here you will find, from the receiver point of view, the first path, for example, line of sight arriving at the receiver, and a succession of different paths with some different attenuation, different delays, which describes what are the different multipaths arriving at the receiver. And when you sum all that, and you change, for example, the place of the receiver, you will have a strong variation of the power, because the combination of all those paths will change the average power that you have on your receiver. So there are some common ways of describing the impulse response of the system with, for example, an RMS delay description, which can represent if your channel have very long paths or very short paths. So it's important, if you want to know if you have a risk of interference between symbols, for example, in your system, to know if you will have a very a path arriving very late after the first path, if you want to equalize on your system. So here are some results of channel sounding expressed in different domains. For example, here you have a description. You can see the impulse response, power delay profile here. So each snapshot represents one combination of different taps, and on a long time behavior. So here it's delay, and on that axis it's in time. So if your channel changes very quickly, you will have different impulse response at different times in the system. Here it's quite stable, but you can have some different results. Here it's a description in time versus frequency. So there you can see in this kind of channel that, depending on the channel that you will use for a subcarrier, for example, you can have a complete different behavior of your link. And here it's a description in distance versus delay. So here you have a moving receiver, and you will see that you have very different power delay profile, with here mainly one dominant path, and after some secondary paths arriving to the receiver. So just to give you some ideas of dimensions that you can find in some different environments, you will see that globally, when you are in indoor scenarios, you will have delay spreads in hundreds of nanoseconds. And when you go to large scenarios like urban, you can have some microseconds delays. So of course, the way that you will try to decode the information cannot be exactly the same when you are in very short delay spreads or very long delay spreads. Here also is an example coming from the ITU channel model that you can use to describe the paths here for the example of an outdoor to indoor scenario. And we have two cases described here, channel A and channel B, which are relative to a very short delay spread, and here a longer delay spread. You can see that for outdoor to indoor, in certain scenario, you can have a very large delay spread. You see here that we are in microseconds, and even at 2.3 microseconds, you will have a very important path, only 7 dB lower than the first path, described by this model. So of course, depending on the kind of environment that you have, this time domain description of your system could be very important. I was talking about coherence time. Here again, I give some examples. You can see, of course, it's relative to the mobility of the user. So if you consider all static, you will have a very long coherence time. But as long as you are moving something in your scenario, it could be the receiver or the emitter or something in the environment, you will increase the Doppler spread, and thus you will decrease the coherence time. So here you can see, for example, that for something quite static with a slow motion, you have some hundreds of milliseconds of coherence time, so your channel still be quite the same between for hundreds of milliseconds. But when you are increasing the speed, you will have a very short time to consider that your channel is stable. So of course, it induces that you have to have a channel state information which is renewed very often if you want to have a good information of what is the quality of the link. Sorry? This is experiments, yeah. Yeah. So just one point, of course, is that when you want to build, for example, a system level evaluation, you want to know not the received power, but for example, the bit error rate of your system. To go from the received power to the bit error rates, an important information is the signal to noise ratio. So to know what is the limit, the threshold in your received power, you need to know what is the noise floor that you have. So just here, classically, we use a very simple formulation, which is this KTB here, which is the thermal noise, only taking into account the temperature and the bandwidth of your system. So of course, as long as you increase the bandwidth of your system, you will increase the level of power that you inject in your system also. So I will skip that. I will go back later. Just want to show you that. The very classical capacity formulation, taking into account the bandwidth and the SNR of the system. So we know that if we want to increase the throughput, for example, of system, we would like to increase the size of the constellation that we use in modulation, for example. But to guarantee that we are able to differentiate all the states in, for example, this kind of QAM modulation, we have to guarantee a very high level of SNR. So, of course, if you use a very robust modulation like BPSK, you can have a very low SNR to guarantee that you are able to differentiate 0 and 1. But if you have a very high order of modulation, you will need to have a very high SNR, but it will correspond, for example, of a very narrow bandwidth with the same amount of noise. So if I go back there, this is an example of a practical WiMAX system on the downlink. And if you search in this table, you can see that all those phenomena that I talked about are taken into account as margin here, because as we are not able to say that we will have always a good information on the channel states, we have to take some margin on the system to say that depending on the fading, so shadowing, fading, possible interference, penetration loss here you have a total margin of more than 20 dB to be able to guarantee that we still have a certain SNR required for the system. So of course, I think you have understood that in the previous talk. The highest noise is the size of the clouds that you have around constellation states. So globally, if you want to describe what is the behavior of a system in terms of bit error rate or symbol error rate or packet error rate, you will use some formulation, mainly based on Markov Q functions, which can translate a certain level of SNR in terms of bit error rate. Here's an example with different kinds of modulation and in two kinds of environments. Here with just white noise, and after here in multipath with relay fading. I will explain after the relay fading. But you can see that, of course, first, depending on the kind of channel that you have, of course, you have better performance in an IWGN channel because you have no multipaths in your system. And secondly, of course, as you have a very robust modulation or very sensitive modulation, the impact of the signal-to-noise ratio is very strong when you are in a 64 QAM, for example. And the important point that we have in all large systems, and particularly in small cell systems, is that we have not only the problem of the channel behavior between the emitter and the receiver, the problem of the level of the noise that we receive also with the system, but the problem of the interference. Because the problem will be expressed not on SNR, but SINR, signal plus noise plus interference ratio. And one point, for example, in this example, is that, of course, you can be interfered not only by an emitter on the same cell that you are using for another user, for example, but also, of course, the size of the interference area of a system is bigger than the size of this coverage area, because even if in this example the sensitivity of the system is given for minus 90 dBm, for example, here, the influence in terms of interference could be down to minus 120 dBm and reduce the SINR here at the cell border and decrease the capacity of the system. So then, what kind of channel models that we can use to describe that further? So there are different class of models that we can use. Empirical models, which is just a more detailed description of the path loss that we have seen before. So you have a lot of description like the old Wano-Kumura Hata, Cost Hata, Wolfe-Shikigami, etc., etc. You have some deterministic models like optical based one or discrete methods. You can have also some statistical or stochastic description of the link, or you can have some hybrids melting some of the previous ones. So just quickly add an example of empirical models. I will more focus on deterministic models. So empirical models, like here in the Cost Hata model, give just a very simple formulation of an evaluation of the path loss between the emitter and the receiver, and this is refined by measurements. So it comes from extensive measurements campaigns in representative areas, representative area of urban dense scenario, rural, forest, etc., etc., and tries to fit with simple formulation like here, depending, of course, on frequency, on distance, but also taking into account the height of the emitter and the height here, sorry, of the receiver. And with some fitting parameter like this CM here, depending on the kind of city that we use here. For example, there's a lot of different expressions depending on the kind of environment. So here it's for urban, and depending on it's a large area, metropolitan area, or medium-sized city, you can have different fits with the CM parameter here. So these kind of systems are very easy to use to predict in very large areas an average value of the path loss, but it's very poorly accurate. Sorry. You can try to describe by statistics law the behavior of the received power in a certain kind of environments. So as described before by the Friis formulation, you can use for the description of the shadowing or fading certain laws. So here, particularly for fading, the very classical one is the Rayleigh fading law. You suppose here that you are completely in non-line of sight scenario. You have a complete angular spread of the path of arrival at your receiver. So you have rays coming from everywhere around the receiver. So it induces a very high level of variation of the received power that you have. You can describe also using a Rice law the variation of the received power that you have at the receiver. So this law depends on a K factor, and choosing the right K factor, you can describe a large range of environments, and the K factor is relative to the weight of the line of sight component compared to the multipath components. So if you have K tending to infinity, you will represent something like an AWGN channel, and if K goes down to 0, you describe a Rayleigh fading. Of course, you have numerous different laws that you can use. For example, Nakagami M laws, which can describe also different kinds of channels. You have also some Weibull laws, etc., etc. So all those kind of laws helps us to describe what is the variation that we can have around the average value, depending on the variation that we will have of the received power of multipath components. But if we want to estimate what is the actual behavior of the radio wave in a certain environment, we must use some deterministic models. So with no averaging, a precise calculation for each placement of the antenna. So we globally have two kinds of methods that we can use. The more classical ones are based on ray tracing. So it comes from optical consideration of the rays. So it's nice to describe large scenarios, but the limitation is that the accuracy of this kind of method is relative to the number of rays that you use and the number of reflection, diffractions that you take into account. So it's a kind of method which needs a real trade-off between the computational loads and the accuracy that you want to have. So it's really well suited for outdoor scenarios. And then you have some discrete methods like FDTD. So those methods are based on the discretization of the environments and the calculation on Maxwell's equation in the system. So it's more complex to calculate, so it induces a very high computational load classically, but it allows to have a very precise and accurate description of the behavior of the link in an environment. So classically, it's more suited to indoor scenarios. So here is an example of a ray tracing system. You have, of course, a description of the environments, and you launch rays from the emitter. You give some weights to each ray depending on the radiation pattern of your antenna at the emitter. Of course, you have a highest weight for the maximum of the gain of the antenna. And you choose a number of rays depending on the accuracy that you want to have. So of course, if you use only a few rays, you will have a poor accuracy, and if you use 10 rays per degree, you will have very high accuracy. But also, the importance is the number of reflection and eventual diffraction that you take into account to calculate the power. So summing all the rays, you can calculate on each point of the map what is the amount of power that you receive. If you use discrete method, you have different systems like FDTD, stands for finite difference time domain, TLM for transmission line matrix, power flow, and AMR-FDPF. So I will describe AMR-FDPF because it's the kind of method that I use personally. So this method is based, as you can see, on the discretization of the environment as pixels. So elementary cells. So the assumption to be able to apply that for the calculation of propagation wave is that the size of the cells is small compared to wavelength. Classically, lambda over 10 or lambda over 6. You have to be very fine in discretization environments. Thus, it induces that for very large areas, it induces a large number of cells that you have to compute. And afterwards, what you do is that you calculate for each cell what are all the flows exchanged with the neighbor. So, for example, from this cell described here, you construct all the links between neighbors, and you propagate, etc., etc. So, this is the principle of the power flow, described first by Chopard. And the AMR-FDPF, it's the power flow method, but used in frequency domain. Previously, it was used in time domain, but the AMR-FDPF gives a formulation which helps to calculate very efficiently and with a reduced computational load this kind of equations. And also the MR of the MRF-DPF methods stands for multi-resolution, because it's based on an aggregation of the cells to enhance the calculation time. So this is just to say that this is a kind of discrete method, but the description is done in such a way that we can have a calculation time reduced and having something comparable to ray tracing or relaunching systems, but with a very fine description of the environment, and particularly taking into account all the phenomena of reflection, transmission, and also diffraction, which is not intrinsically implemented in relaunching or ray tracing methods. So this is just an example of the software developed around this method, which is called iPlan. And here, in indoor scenario, you have an access point, so you can see all the diffractions, transmission, reflections, etc. in the environment. This kind of method is also easy to use when you have a multi-floor building, because we can easily propagate the waves from one floor to another one. So this helps when you have a very sliced building, because you can use only 2D propagation and propagate vertically only the sources from one floor to another. This kind of method is more efficient for this kind of indoor scenarios, like I said before, than outdoor scenarios where you have to privilege ray tracing tools. One of our interests of this kind of method, globally discrete method, is that as you have a very fine description of your environment with a pixel very small compared to the wavelength, you can also try to extract some more statistics of the propagation that you can predict. So for example here, if you take a snapshot of the propagation calculated with this kind of tool, you can use a fit of the distribution of the received power that you have in a small area and fit it with some laws, like I've given before, a Rayleigh or a Rice, a Nakagami law. And using that, predicts what is the kind of bit error rate behavior that you will have. So this is the base to be able to connect this kind of tool with system level tools to transcript a coverage map, not only on average power, but also on distribution laws, to be able to have a fine description on the potential bit error rate that you can achieve with this kind of system. Okay. So if you just give an average power, not taking into account if we have an AWGN, for example, or ray fading, the performance in terms of bit error rate could be completely different. So this information is really important to be able to have an efficient prediction of the quality of the link. If we go further in the information that we need to describe some femtocell behavior, one important point is that while you will use OFDMA, you will have a wide set of frequencies that you use and you want to allocate those frequencies to different users. So the wideband description of the link is also very important, because if you consider that you calculate only for one frequency and you suppose that it's the same link for all the frequencies, you're completely false. So here's an example of a comparison between a measurement campaign which was done in Stanford University and the simulation that we can give of this environment with this tool. And here the purpose is to be able to predict the kind of variation that you have in terms of frequency. So here it's in the 2.4 gigahertz band. So I will not discuss each link separately, but globally the idea is that if we want to have some prediction tools, we don't want to know exactly what subcarrier will have this kind of SNR, but globally what is the statistical behavior of the link. But not only for one frequency, but for all frequencies. So for example here, one criteria is the fading depth that we will have, but we want to have globally the same behavior in terms of average power on the band, but also to know if in that band we have a very fast variation or not. For example, if we can aggregate some subcarriers, considering that the behavior will be the same for a block of subcarriers, or if we need to have a perfect knowledge of the channel for each subcarriers. Okay, so with this kind of link, we can, we can have a knowledge about the wideband statistics of the system. Same thing for the shadowing. We can try to extract shadowing information from measurements, of course, but also from simulation. So here you have the same principle. You take some information about the received power at different points, different distance. You subtract the mean pass loss law that you can calculate from the averaging of all the value, and then you can extract the values of the shadowing that you have in your system. So with this description, we can have a very fine description of the fading before, seen before, or of the shadowing, and of course of the pass loss. So we can offer a complete description of all the phenomenon with this kind of simulation tool. Well, for the time domain statistics, as we have wideband simulations, we can also give the transformation in time domain and reconstruct the impulse response of the system. So here you see, for example, the long time behavior of the link, and you can compare. It's a comparison here between measurements and simulation, and we can have a good fit between the impulse response that we have in simulation compared to the measurements. Same thing for the coherence bandwidth. You can compare what are the simulated values and the measurement values. So let's move now to some Femtocell issues. So globally here, this slide summarizes, depending on the kind of scenario that we have for downlink, uplink, femto, macro, etc., what are the kind of problem that we encounter, and what kind of tool that we can privilege to investigate that. So you see that most of the commercial tools are based on ray tracing system, but often it's also combined with statistical information to increase the accuracy of the prediction. So you see that if you want very high accuracy, you have to give some deterministic description of the system with ray tracing of discrete method. And of course, if you do that, you have a very slow calculation of your system. And as long as you want to have a very fast description, you will have to simplify that. But if you simplify too much, you have just a free space formulation with no accuracy at all. Yeah.
As you said, that means to use this method, we need to divide the coverage area in very small cells.
Yes.
Smaller than the wavelength.
Yeah.
So
of course, you have some methods that you can use in large areas using what we call fake frequency to calculate that multiply of the wavelength to reduce the complexity and using calibration afterwards to recover a fine accuracy. But as long as it's indoor scenarios, even on a classical laptop computer, you can have calculation of
a room
indoor propagation. But if you go to outdoor scenarios with very wide area, yes, here it's very heavy in computation and particularly in memory. So
it's about the indoor or outdoor environment, or it's about the area size of area, because when we say indoor outdoor it means the particular environment.
The work I presented before on iPlan simulator is mainly on indoor system.
Okay.
So I will just discuss there the combination on outdoor, indoor, outdoor, and what are the methods that we can privilege for that.
But I'm trying to understand what information we need to provide about the environment to this tool to use this finite difference method. Means for every means we need to provide a three-dimensional information?
No, not necessarily. It's mainly if you describe walls with all materials, it's enough. You do not need to describe furnitures, for example. That's the point that I want to discuss after. If you want to take into account further, you will have to combine this kind of deterministic description with statistic description. So globally, if we want to describe shadowing, you can extract from measurements of simulation some log normal variable values. The problem is that you will have, depending on the kind of environment, level of shadowing with a lot of changing. So for system level simulation, measurement campaigns cannot be performed every time. So this kind of tools that we can use coming from deterministics resolution of the environments can help us to construct some database of the possible shadowing values that we can encounter in certain scenarios. Same thing for the fading. When we have discrete method, we can use the fine description on the space variation of the receipt power to construct some laws based on Rice formulation, classically, to give, for example, the key parameter of the Rice law to be able to compute the bit error rate of the system. Here's an example of a study of Femtocell deployments done by the University of Bedfordshire. Here, on this first graph, you have only 2 macrocells in the environment, and here you have the small lights here are femtocells deployed in certain buildings. So here it's just a coverage map, so considering that there's no interference, just telling where is the highest level of power received from the macrocell or from the femtocells. So of course, obviously, if you add some femtocells in the environment, you guarantee a better coverage of the system. Here it's another way of depicting this principle. Of course, if you add some femtocells and you suppose that you operate all that in order that you have no interference, of course you increase the quality of the link that you have. Yes?
And you have this transmission of, say, femtocells,
Now, of course, the transmission of femtocells would act as interferers for the macrocell users.
Yeah, of course.
So there would be some coverage holes, probably some coverage holes there. So you're filling coverage holes somewhere, so it might lead to some new coverage holes in the macro area.
Yeah,
so
that's exactly what you have here.
Okay.
So this is not taking into account only the coverage, but the SINR. So here, you see that you increase the contrast, in fact, of the picture that you have, because, of course, you will have a very good areas where you have femtocells, but you will have very bad areas surrounding the femtocells because you have interference there between the macrocell and the femtocells.
Thanks.
Okay. But, of course, this is well known. Here is just a tool to describe that. So for the particular case, the particular problems that we encounter when we try to describe correctly with this kind of tools the behavior of the links, there's two main problems, going from outdoor to indoor, and the reverse problem from indoor to outdoor. So, yeah.
Do you do any kind of like, do you take into account that you adjust power, or you take any kind of interference management you do, or just assume that the femtocells are transmitting with a specific power?
Here is really with no other assumptions that equal power and no management at all.
Okay.
It's
Okay.
only SNR, root of
Okay.
SNR.
Okay, thank you.
Yes.
And what about the minimum coupling loss? Is it taken into account?
The minimum what?
The minimum coupling loss.
No, no. Here you have just each femtocell is independent on the same frequency, and you have all macrocells and femtocells using exactly the same. So there I present a joint work in the field of the iPlan project, where we have conducted to try to link two efficient tools. One efficient tool for outdoor scenarios, which is based on ray tracing, which is ILA, and our tool developed for indoor scenarios. And we link these two tools. It was not totally easy to do because, of course, to give sources for indoor scenario, we need to calculate with the outdoor scenarios all the rays coming into the building. So we sum all the rays at the boundary of the building, and we use the calculation, the complex value of the field that we create on all part of the building as sources for the building. So here I present you the city laboratory, which is here. And we do some measurement campaigns to validate the simulation. So here it's a ray tracing tool. So the emitter is here. We launch all the rays. We calculate the received fields that we have on all the walls. And after that, we use the information as sources for the indoor propagation with MRF-DPF. And we compare here simulation and measurements. You can see that there's a very good agreement between simulation and measurements. And we calculate the root mean square error between simulation and measurements. And we have something less than 3 dB, which is very good. And as you can see, with this hybrid method, requiring only a calculation time of less than 2 minutes. So it's very fast, and it's on a classical laptop. So this could be a very nice solution to evaluate this kind of scenario. Here, this is the results for 2.4 gigahertz. And we also conduct a campaign at 3.5 gigahertz, and we have quite the same kind of results. But the remaining problem is for the reverse scenario, because indoor to outdoor is more difficult. Because when we use MRF-DPF as the indoor tool, we have to calculate on each walls the equivalent rays coming out from the building. So we have to use some SAGE algorithm, which is a well-known algorithm to describe in terms of direction of departures of the rays of an array of antenna, for example. So we use that to calculate all the rays that we use afterwards for the ray launching system, and we can then calculate the coverage map outdoor with that. So the results are less accurate in that that scenario. The main reason of that is that for the moment we have used 2D formulation for the indoor scenario, and so the description of the rays outdoor are only given in a 2D plane. So we have, as we have done some measurements at a lower height, we have some less good accuracy of the system. Yes, you have a question?
In this simulation, are you taking into account moving objects inside the room?
No,
or?
it's all static here. Everything is static.
Okay.
How do you decide on the number of rays?
The principle of the relaunching system RLA is that it's adaptive. So you have some calibration points used to adapt the number of rays for a certain accuracy that you want. Okay.
Excuse me?
Yeah.
So I just have a basic propagation question.
Yeah.
It's not directly related to maybe femtocells, even though it's a part. So when we say that the rays propagate through the wall, we generally give a ballpark number of say 10 to 20 dB losses, right? We say that okay, it incurred say 10 dB loss.
Yeah.
Where does that energy go? From physics perspective, is it like heating the material, or where that energy is really going?
Yeah, it's when it's losses, it's like a thermal phenomenon that you have some energy taken from the material. Yeah.
So actually, I was reading about it, and so the source which I probably read, it said that it's basically the moisture in the walls which is really the most important criteria which decides what the losses are. So what are your views about it?
It's true that for all materials, it strongly depends on the fact that they are dry or wet. You have a very strong difference because the water is very lossy.
Right.
So everything when you have a wet material increases losses.
Okay. And that was just a digression. Thanks.
Okay. So where I was there. So I want to finish on some examples of existing commercial tools. It's not exhaustive, but I have some information from some colleagues on certain tools. So this is the tools developed by Runplan, which is a partner of the iPlan project. So they developed the IBLNet software, which is a big software going from the propagation to the system level evaluation of the performance of a network. So of course it's not restrictive to femtocells, but it has been developed also for femtocells, so it can be used for wireless LANs deployments or CT deployments, etc., etc. So this kind of tool can be used also for multi-floor buildings. So it's based on a relaunching tool which enables to describe the propagation indoor. It requires calibration to fit correctly the transmission between all the floors in a certain building, because the interfloor attenuation is very depend on the kind of materials that you use also. So of course, it depends on the kind of building that you have. You can have attenuation of only 8 dB in certain buildings and 20 in others. So it's really important to calibrate for that. And also the interest is that you can use this kind of coverage map description linked with system level evaluation to compute what is the quality of service of a certain system. It has also included some optimization, automatic optimization of the placement of access points, for example, for wireless LANs. So you can see here an example of first coverage, and after optimization, the placement of third access point to ensure a perfect coverage of the area. So here it's only based on coverage, so average power. So as I discussed before, the interest in this kind of tools, it's one of the main goals of the collaboration that we have in the iPlan project, is to enrich this kind of tool with statistics, not only mean power, which is a good information, but it's not enough. It's not because you have a mean power of minus 50 dBm that you can guarantee that you have always the good throughput, because it's around this mean value you have a very strong variation. You will lose frames all the time, and so you will decrease the throughput. So this is something which can be included in this kind of AMP system. Of course, if you consider the interference between systems, you can also try to optimize in terms of ISINR. This is the example here. You have here a strong interference zone between two access points, and you can try to mitigate that and to have a nice behavior of the access points in the same environment. Here is an example of the use of this tool for femtocells. So here you have a macrocell antenna here in a residential area. So you can describe the propagation outdoor and so the propagation indoor at different levels of the houses. And you can see here that if you put some femtocells in the houses, you have a very strong leakage of the waves outside, and then this can, of course, lead, like we have seen before, in strong interference, so degradation on the coverage outside, because we have strong interference potentially between femtocells and macrocell. You can also use, of course, that tool to mitigate this problem by confining the waves inside the house, by choosing the right placement of the antenna of the femtocells to ensure that the leakage are lower than before. So you can use that to reduce the interference outside the buildings. One point is also that this tool can be useful in very high buildings when you want to have some scenarios where you have some lower building and higher buildings, and you have, for example, antennas on the rooftop. You can also use this, as it's a complex and big problem to calculate. You can perform it with that tool. So I will not detail all the results that you can achieve with that, but globally you can study also some scenarios where you have very different heights. So it's also, I think, important for the future deployment of a lot of femtocells, because the classical view that it's more easy to calculate of residential areas where you have a very flat network and a very regular spacing of the houses, it's not as complex. And when you consider high buildings where you have multiple floors and you can have eventually hundreds of femtocells very close to each other with different floors, I think there the problem of interference will be very, very complex to evaluate. And I move here to another tool developed by Cyril. So it's another company which commercializes Volcano software. Maybe one of you know that software. So they have developed also different methods to try to evaluate from the system level the performance of the network. So of course, here again, we cannot use the same method to compute all the kind of environments. So Cyril also uses some retracing methods for outdoor scenario, but combine it with statistical methods to add some fading statistics around the results and to try to evaluate what is the combination of the outdoor-indoor scenario. We also have an intermediate complexity system using relaunching for the outdoor and multi-wall propagation for the indoor, which is a quite simple way of calculating only the attenuation of successive walls of the same ray. And in that study, they use an analytical expression of the path loss that you have to evaluate some femtocells. So as you can see, it's exactly what I discussed before. It's a very simple description with a very symmetric description of all the walls, etc. It's not really easy to calculate that. So it's the first theoretical study that they have developed, but they transpose that also in a large area scenarios. But there, they use their method of dominant path to reduce the complexity in a large area, and they try to improve, but they are still working on that method to be able to predict in very large areas the interference between femtocells and macrocells. So here the example is the comparison between two placements of the femtocell in the building close to the window, where you have a very strong leakage, and more deep in the building when you can reduce the interference that you create outside. And they also use some statistical models to take into account the time behavior of the link, also the frequency behavior of the link, and they combine that with their optical system. Okay, I will skip that. Just to finish on the last example on WindProp, which is another simulator from AWE industry. So they also use ray tracing for outdoor. There they also use a different ray tracing, simplified ray tracing for indoor, and they combine that. So that's interesting because it's exactly what I described before. I think the best way to describe this kind of link is to combine deterministic approach like ray tracing with some statistical description of the fading values. Here they use a Rician distribution, and they use a fit on a particular K factor depending on the kind of environment that we used. For example, here they use a K factor of 1.5 for the femtocell indoor scenario. And as you can see, for the macro cell propagation, they use a different K factor of 5 with also two different mobility models leading to different Doppler, so different occurrence time. And they can compare the influence of the macrocell on the femtocell. So here you have the example of one femtocell in an enterprise building compared to two femtocells, and here with the ratio compared of the power of the femtocell compared to the power of the macrocell. So of course, here, with only one femtocell, we have some zones where we cannot achieve a good quality. The criteria that they use there is -16 as a limit. So here you have two zones with no coverage, and with two femtocells you can reduce to approximately all the building having a good coverage. There. So I finished by concluding on that, of course, it's not a simple problem to evaluate femtocell scenarios, because there's a lot of complex physical phenomena to take into account to model the behavior of this kind of links. So this kind of tool that I've described could help to give some throughput capacity information at system level simulator to give better performance evaluation than only considering empirical models. But the limitation of deterministic models is that they are static. So if we want to have a better performance on the evaluation, we have to combine deterministic models with statistical models. So to be able to describe that everything is not static, you have some mobility, you have some furniture, so we have some statistical laws to add around the value that we calculate with the deterministic method to be able to give the range of the variation that we have. So what I would propose as best scenario is to use retracing methods for outdoor scenarios, for indoor scenarios, discrete methods, so to combine those methods and to add around that statistics of the link. There is. Thank you for your attention.
Okay, thank you, Guillaume, for your presentation. We can take 2 or 3 questions.
Are all of the tools you mentioned, propagation ones, commercial? So can you name some open source analogs, maybe? So
speak louder, please.
Are all these tools you mentioned, the propagation tools, commercial? So probably you can name open source analogs if they exist, really.
Honestly, I don't know open source.
Okay. Thanks.
But I'm academic, so I'm not. I'm not selling tools, but no, I don't know open source propagation tools.
Maybe these tools are some kind of open for scientific community, no? So
yeah, of course. For example, the MRFDPF method that we have developed, it's an academic work, so we can collaborate without problem and without charge on the software. But for the iBuildNet, WinProp or Volcano tools, yes, there you have to pay.
Okay, so I have seen in most of your simulation you're focusing on femto interference on the macro users. What about the other way around? Have you noticed like there is the macro user effect on the femto, or it's not that significant?
Honestly, I cannot give some numbers on that because I'm more interested in the physical phenomenon and how to describe it. So for the system level evaluation that you can use after to evaluate this problem, I'm not the good guy to talk to you about that. So no, I cannot answer that question. Honestly, of course, we can perform some simulation because, as I've shown, this scenario it's the most easy to compute for us because the outdoor to indoor is more easy to compute than the reverse problem. So I think the evaluation of this kind of interference it's not a problem to perform. But I cannot give you some numbers on that. Sorry.
Okay, thank you.
Hi, thank you. I would like to know what is your opinion when you have to simulate MIMO channels. So we need to have more antennas, more propagation, more.
Yeah, of course. So it greatly depends on the tool that you use. When you use relaunching tools, the complexity will be relative to the number of sources that you use. It's quite simple. It's purely linear. When you use some discrete tools, like the one I have shown we have developed, you have two separate phases of the calculation, because you have a pre-processing of the environment and afterward calculation of the propagation. So in this kind of scenario, the good thing is that the propagation phase is much more quicker to calculate than the building of the environment. So once you have pre-processed on one environment with this kind of method, you can quickly simulate a lot of different sources. So the evaluation of MIMO links, it's not really difficult with this kind of links. Also, the problem is that if you use ray tracing for MIMO links, you need absolutely, because I will not detail that, but you can use ray tracing with only magnitude information on the rays, and you can use ray tracing with complex information on each rays. Of course, if you use complex information, it increases the complexity. But if you want to go through MIMO, you need the phase information to be able to evaluate the diversity of your system. So, of course, you have to use a complex formulation on the ray tracing. And with discrete method, it's intrinsically complex, so it doesn't change anything to use it for MIMO. It just increases the number of propagation phase you have to do, but for the global calculation time, it's not increasing too much the system.
Okay, thank you very much. I think with this we conclude the first presentation of the afternoon. Now we have the coffee break, and in parallel we have the poster session, so I invite you to take a look. Okay, see you in half an hour here.